Well, welcome back, guys, and I do hope, as ever, you and your family are keeping well. So, this is your penultimate lesson, I think, on gravitational fields. And what we're going to look at today is a little bit about energy. So we're going to look at the physics behind gravitational potential. So to begin with, we'll use some physics that we've done already. So it's a little bit of a recap. So we're going to look at Newton's law of gravitation. Now, if you remember, the force between any two bodies that are attracting each other due to a gravitational field is proportional to the product of their masses and inversely proportional to their separation squared. So we had F equals minus G m upon r squared. Okay. Remember that the minus shows that the force is towards the mass and the r is moving away from the mass. The other thing to note, if you remember, is it doesn't matter which way round you put the masses, but typically big M is the one that you'd visualize as doing the attracting. I appreciate they both attract each other with equal and opposite forces, but you know, that's going to be the Earth and that's going to be us. That's going to be the Earth and that's going to be a satellite. Okay. But let's take this a little bit further, because you know, again, GCSE, always bring back your GCSE ideas with fluency, please, that energy, work done, is force times distance. So let's times this force by distance. So we'll get the energy will be equal to FR, so one of those R's comes to the other side, which will be equal to G m upon R. And there's the minus sign, just to indicate the direction that things move, though we usually don't bother with that at this stage. But it's actually quite important later on. Now, that's easy enough. But hang on, if you think about it, if you've got something in a gravitational field, it probably won't be a kilogram. Okay, so it might be interesting to know how much energy does it have in the gravitational field per kilogram. Okay, so per kilogram of the material. So let's divide by the mass of the thing that we imagine being attracted to the more massive, the larger object. Okay, so the energy per kilogram will be equal to FR, the energy, per kilogram of object, and that will be equal to minus G m upon R. Okay, so this is beginning to tell us something about how much energy something has in a gravitational field. And you'll notice there's a minus sign in there. I had a discussion with one of my students the other day, actually. How can energy be negative? Okay, because it's not a vector quantity. Well, we'll come back to that. Okay, we'll come back to why it has a negative value. Now, this is where you need to be a little bit flexible with other physics you might have done. Okay, because we're not going to write FR upon M every time. We're not going to write energy per kilogram. Okay, we're going to give that lot a symbol, and we're going to give it the symbol big capital V. Okay, I'm going to call it V subscript or sub G, and we know that that now is equal to minus G m upon R. Now, what I meant about being fluent with your other physics is that this V sort of comes from voltage. Okay, and you might think, well, hang on, what's this got to do with voltage? But if you remember, electrical potential, okay, and potential energies when you're looking at electrical systems, the voltage is measured in joules per coulomb. So that's kind of forces between charge things, okay? And we'll do electric fields in detail later on. But this is not a joules per coulomb, electric fields. This is a joules per kilogram. So we kind of steal the letter V, but we put a little g there to remind us that we're talking about gravitational fields. Okay, and what you'll notice is that the energy that an object has moving away or away from a large mass, okay, Vg is proportional to the large mass, okay? So when we deal with the negative sign, you'll see what that means. But if you think about something that's fallen down to Earth, okay, it needs energy. It needs gravitational potential energy to get it away from the Earth. And if the Earth is more massive, it will have a stronger gravitational field, and therefore you'll need to feed in more energy to get that object away from the Earth. Okay? You'll also notice that Vg is proportional to 1 over r. So that's really important, because what that means is that as we back off from the mass that we consider to be doing the attracting, as the separation between them becomes bigger, the change in energy as we move further and further away becomes less and less and less. And I'll just remind you about why that is. That is because of the radial nature of the field. Do you remember the point mass has this kind of field around it? Okay, I'll add a few more field lines. There we go. And I'll make sure I draw the direction. And remember that the field lines don't go through the mass. Okay, we always stop it at the surface, because we have to imagine a point mass. And if we let them go into the middle, we'd have an infinite gravitational field at the midpoint, which doesn't make sense. But I haven't drawn this very well, because that line, they should have all kind of line up. But the point is, you can see, do you remember these lines separating as we move away? So you can see why the energy needed to move a meter when you're much higher is less, because the field lines have spread out more. So let's now deal with why Vg is negative. And it's really important you understand that it's not the potential energy of an object when it's up here away from the Earth. It's the gravitational potential, which means it's the amount of energy per kilogram of that object. And that doesn't change if you change the object. So if you think about it, if you move up 1,000 kilometers from the Earth's surface, for example, if you're 1 kilogram or 2 kilograms or 10 or a ton, it doesn't make any difference to Vg, to the potential at that point, because it's defined in terms of the number of joules per kilogram of that material. So I'm digressing. So let's deal with the negative sign here. Okay, well, we need to define Vg. Okay, remember that's a little subscript. I've got to be really careful that looks like a subscript. Some teachers probably correctly sort of do that sort of thing to say, look, it's just down at the bottom to remind you. Okay, so remember that if we define things in physics in terms of a statement, we don't use units. Yep. That's because our friends in America probably aren't in this case, but could be using inches, we could be using meters, etc. Okay, but the definition of Vg is the same for everybody. Okay, that's really important. The formula will be exactly the same as well, apart from there'll have to be dimensionless constant in there to sort out funny units. Okay, so let's define Vg. So what we do is we define Vg, yeah, V sub g at a point. Okay, so we pick a place near a gravitational, far away from a gravitational mass, and we say, right, how many joules per kilogram would an object, being careful by what I say about have, wouldn't have, okay, because of the minus sign, is short of. How much energy is it short of? Okay, and you'll see what I mean by that. Okay, so Vg at a point is the energy needed. Yep, that's the important thing, giving the object energy needed per unit mass. So there we go. You can work in any units you like within reason. Okay, and here's the clever bit. To move the object from, and here's where it gets interesting, to move the object from infinity to that point. Okay, so think about what that means. That if you have a Vg value, okay, that will be the energy that you need per unit mass to get that object from infinity to that point. Now, if you think about it, if you're really thinking about the radial field, I hope you appreciate that, and this is sort of bad teaching, but I'm going to do it anyway, that you don't need to give it any energy. Yeah, it will kind of fall in. It'll be attracted by the large gravitational mass. So what do we mean by the energy needed to move it to the, from infinity, from a long way away, in towards a gravitational mass? Well, of course, the reason it's minus, and you might want to replay this bit again if I get it clearly across to you, the reason it's negative, of course, is as it falls in, it loses gravitational potential energy. It gains kinetic, of course. Okay, in a frictionless system. So we don't need to give it gravitational energy to move it from a long way away and closer to the object. We get energy out. We lose gravitational potential energy, so that's why there's a minus. It represents the energy that it doesn't have anymore. Okay, it's interesting to note that the minus, you can see where the minus comes from now, but Vg is a scalar, okay? It's not a vector quantity. And one of the ways that we look at this is, where shall we set our zero of gravitational potential energy? Because is it going to be a different place for every mass in the universe? No, it isn't. Okay, I'll change colour. Yeah. Let's just define far away. Yeah. Don't get hung up by what I mean by infinity. I mean, you don't have to somehow find some edge to the universe or something like that and say, okay. If you think about the radial field, okay, it's spread out massively once you go a long way away from a gravitational mass. And we're doing two masses here, you know, not a whole solar system or a galaxy or something like that. Okay. But at infinity, let's set the energy, yeah, that is potential energy. I'll write that as PE. Okay, I suppose it's GPE really, isn't it? Let's set that equal to 0. Okay. Now, again, I had a conversation with a student about this the other day, and it was like, how can something have no energy? No, it isn't like that. Okay. We just say, a long way away, it's got no energy. Yeah, a long way away, it's got no energy. And as it falls in, it speeds up and loses gravitational potential energy. So it's given out potential energy, or more correctly, it's converted it to kinetic. Now, if you're still not clear on that, what about this 0? People keep asking me. Okay, it's purely a device, a mathematical idea to make one place the 0 in space, wherever infinity is. Infinity is a long way away from other gravitational masses. Okay, so I'd like you to think of that point as being similar to, I said it the other day to one of my students, to me standing on my lab floor, and if you know where I work, I'm on the ground floor, okay, and I'm just going to call that 0, okay, I'm going to call that ground 0, yeah, the 0 place, and I'm going to define my energy, my up energy, my gravitational potential energy as being 0. So if I go upstairs to biology, I gain gravitational energy, but this is all about the energy needed per unit mass to move the object from high up to that point. Okay, so if I call this area 0, then if I'm in biology, as I come down from the new 0 that we're defining, I lose gravitational potential energy. Now, another way of looking at that, if you want to visualize it the other way around, is let's make the floor 0 now. Okay, so we've gone through a stage of saying the floor 0, then biology 0. Let's go back to making the floor 0 and I go into the basement. That might be a better way of visualizing it. Okay, so let's call this 0 height, more importantly from the center of the Earth. Okay, and as I go down into the basement, I definitely have less gravitational potential energy, and therefore my gravitational potential energy value there will be negative. So we're clear now that Vg, is the energy given out by a mass falling to a point at position R, okay? Now, there's a really good way of thinking about this, and I'm going to keep it a bit simple because this is the sort of thing you do at detail probably at university. But imagine space being like this, okay? Being like a well that you can fall into. I'm not suggesting that I've got the curvature right here, but I'm just kind of making a point. Okay. Now, some of you might have heard of curved space-time and things like that. I'm kind of not going there, but you can sort of see, as an aside, that if you're at infinity and you're travelling along this way across the universe, okay, on this diagram that would still be infinity, you kind of would get pulled, I'm trying not to say sucked into this, but pulled into this by a gravitational mass here. So I'm going to put the large mass there, M, and I'm going to imagine our little object out here at infinity. So there's our other little mass, okay? And by definition, this point is the 0 point, okay, of energy. And then we'll let it fall in towards the gravitational mass. So it will fall in. Or more interestingly, what would happen if it was a satellite and we just positioned it there in that orbit around this mass? Hang on, that's not the orbit. I hope you understand that that's the distance away from the mass. So you can see we've got a distance here of r, and therefore if it had 0 gravitational potential energy here, because the gravitational potential, the joules per kilogram, is 0, then it's got even less here when it's this far away from the mass. And this shape can be drawn correctly and represent how the radial field changes, or more correctly, how the gravitational potential changes. Now, there's another way of thinking about this, that you could say that at this point R, the object has kinetic energy. And here, Vg at that point, which will be a negative value, okay, will be the kinetic energy per kilogram of object, because clearly it's got none here and it's gaining kinetic energy there. But because they're interchangeable, of course, the gain in kinetic energy will be equal to the loss in gravitational potential energy. So this is a really good way to think about it. And just stop for a minute and check that you understand why now we set infinity to be 0 and why gravitational potentials, and later on gravitational potential energies, will be negative values. So, would you believe, as I was setting up the filming there, a spider was quite a large one, was climbing up a thread this way. So I wonder if he joined our physics lesson and actually appeared in the video. I don't know, but I've kind of chivied him off to go somewhere else. Right, last little bit on this. Something I find really, really helps with this is the concept of equipotentials. Okay, places of equal potential energy per kilogram. So the way to think about this is, and I'm going to draw this quite small. Here's the mass that's doing the attracting. Okay, and you remember that it's got this field that comes like this. Got to be careful. I nearly said coming out of it. Of course, field going into it. Yep. I'll draw a few more field lines. There we go. So there's the radial field. I'll leave off the direction for a minute. Okay, funny, we're talking about spiders, look at that. What I'd like to do is to draw this ring here. Now, if you think about it, this ring here is always the same distance away from the gravitational mass, and so it always has the same gravitational potential. It's a place of equal potential, equipotential. And I found these really useful ideas when I started sort of learning physics when I was younger, both for all kinds of fields, but particularly for electric and gravitational fields. So let's draw that position here. Okay, it should be a nice circle. I haven't done very well there. Now, let's go out a fixed amount, and here's, the next equipotential. Okay, so I hope you notice that that gap is smaller than that gap, and these two gaps aren't the same. So then I would always get students maybe to come up here and draw on the next equipotential, but the next one is not here, it's about here. Okay, I might draw an equipotential on the Earth's surface. Okay, so if you remember satellites will whiz round an equipotential. They won't gain or lose kinetic or potential energy. Okay, now because you see the gaps getting bigger and bigger and bigger because of the radial field, doesn't it nicely show that the gravitational potential, put that in brackets, is proportional to 1 over r? And I think this diagram shows it nicely. Okay, so if you go up in equal steps or step changes of gravitational potential, you will have to go further away than you did last time, and then further, and then much further. Okay, because what you're doing here, is looking down the barrel of this one. You're seeing rings close together and then spread out and then really spread out. So I hope that's a useful way of thinking about how gravitational potential changes away from a large gravitational mass. So now let's put this to use and do a little calculation. So what I thought we'd imagine that we're doing is we're going to lift me from the Earth's surface in a spaceship to infinity. Okay, and it would be interesting to see what gravitational potential difference is that, because if we know the joules per kilogram, then we can work out how many joules will be needed to get me from the Earth's surface to infinity. Okay, so let's lift me. It could be you if you want. Probably a different value of mass though, with respect. Okay, lift me or you to infinity. So we need a little bit of data for this, and I weighed myself this morning. So my mass, so that's the little m, remember? Okay, not the large one. Okay, the mass of me, so m sub fj, 57.3 kilograms. Let's do the unusual thing and round up my mass. So my mass is 60 kilograms. Okay, we'll have g. Not suggesting you can memorize g, and you can't memorize its units, but a very small number, because gravity is a very long range but very weak field. So 6.67, going to make the point clear, times 10 to the minus 11. Okay, Newton meters squared, kilograms to the minus 2. I find it hard to visualize what those units mean. Okay, remember that the radius of the Earth, I'm going to start off from the Earth's surface, and that is just over 6,000 kilometers, 6370 kilometers. Okay, remember that's in the wrong units for us. And finally, the mass of the Earth, so appreciably larger than my mass, 5.97 times 10 to the 24 kilograms. Okay. It's just worth saying at this stage, by the way, you probably won't remember those numbers, but it's quite nice to remember in SI units. It's quite nice to remember the orders of magnitude. So if some crafty like me, interviewer at university says, could you just estimate okay, you won't be scrabbling around for a number. You'll go, well, the mass of the Earth is approximately 1 times 10 to the 24 or whatever. I know, more like 1 times 10 to the 25, but you get my point. And I think certainly I don't do university interviews, but if I did, I'd be impressed if you kind of pulled the sort of ish number out of the sky and you could do a bit of a calculation just in your head using the orders of magnitude. Okay, obviously in the exam calculator, work with every single decimal place on your calculator, okay, right to the end, and then do a sensible number of significant figures. Don't round every time, because you'll get a rounding error. Okay, so I'll just remind you that I'm being lifted from the Earth's surface to infinity. So that potential well, how much energy would you have to give me to get me out to infinity? And if you think about it, one or two of you will struggle with the concept, and so did I, to get us to infinity. Well, doesn't that mean that R gets bigger? Because if it's infinity, then we get to infinity and then we have to go further. No. Okay. What we mean really is the place we define as 0. And at infinity, the gravitational field equipotentials, will be spread out infinitely largely. So it doesn't really matter. Okay. It's a kind of theoretical concept. Okay, so remember that, change colour, VG, is equal to minus GM upon R, okay, and so if we put numbers into this, that will be the energy that I am short of on the Earth's surface per kilogram, so you know how much energy you need to give me to get me to infinity per kilogram, and if I'm 60 kilograms, you know how much energy in total. Okay, I'm going to say it again. You're tired of me saying this. That R, okay, is not has to be done very carefully. Remember, it's from the surface of the Earth. Okay, so be careful that you work in meters. But this R, is where I am positioned. So for once, it is this value in meters, not kilometers. I am on the surface of the Earth. It's not, as some students think, we're going to infinity. Okay, so we've got to put infinity in here, which would be a really bizarre thing to do. Okay, R is the position of the mass in the gravitational field. Okay, from the centre of the larger mass that's doing the attracting. So have a pause there. Okay. And see if you can work out how much energy I would need per kilogram, okay, to get me to infinity. And then it might be interesting to work out how much energy I would need to get my whole mass to that point. Great, so how did you get on? So I hope you had a calculation that looked something like this. So the energy that you'll need to get to infinity. Okay, more correctly, should we do the energy you're short of at the Earth's surface, okay, at R? So 6.67 times 10 to the minus 11, bear with me here, that's G, times by the mass of the Earth, 5.97 times 10 to the 24. Okay, I'll get a ruler, and then let's divide that by how far away we are from the gravitational mass pulling us in other words, on the Earth's surface. So 6370 times 10 to the 3. Okay, be very careful not to square that number. You can forget what you're dealing with here. We're dealing with gravitational energy, not forces. Okay, I don't know what to say now about calculators, but for heaven's sake, get this right on your calculator. Okay, I don't think you can get it wrong, but I know that some modern calculators will do. Now, what will they do? They'll do that number. No, I don't know what they do. They really confuse things. I think in this case, you should be fine. You should have, do you remember my interview thing? You should have in the back of your head a kind of ballpark figure of what it should be. It should be in sort of a few tens of megajoules per kilogram. So VG, I hope you got, was 62 0.51, I'll go to 2 decimal places here, times 10 to the 6 joules per kilogram. Yep, did you get that? Okay, and then if you times that by my mass, okay, the energy that you will need to feed in, yeah, is equal to approximately 3.75 times 10 to the 9 joules, and that's for 60 kilograms of payload to get to that place. So I hope you got that right. If not, have another quick look over it and make sure you get it sorted, because it's the sort of thing that does come up at A level. So now let's look at things graphically, as we always seem to in physics. So I'm going to draw a graph of the gravitational potential from the centre of the Earth to infinity. Okay, so the first thing I have to remember is that the axes will be negative. So I'm going to draw this shape. And I'll take you through every little bit of the graph as we go along so it makes sense. Okay, so this axis, the y-axis, is going to be the gravitational potential, and if you remember, on the Earth's surface it's about 63 megajoules per kilogram, so we'll do this in megajoules per kilogram. Okay, and then we'll do distance from the Earth. Okay, so this axis is going to be an r-axis, and just for interest's sake, it's a bit of an odd unit, this. I think it's an unfortunate coincidence the way the prefix works here, but let's do it in megameters. Okay, so megameters. Now, you can see straight away that that looks like the two masses or something, but if it's written like that, be sure that you appreciate that that's the units, okay? And you might want to make a little note there that that's megameters. Okay, so let's position the Earth fairly obviously at r equals 0. So there's the Earth. And it's going to be for a single mass, this one first, okay? So the Earth has a size. So I'll draw a little bit to represent the radius of the Earth, okay? And I'll position there 6.4 megameters for the radius of the Earth. Okay, so 6, let's make that point there 10. Okay, let's make this point here, gonna have to go to here, 20. It's not easy trying to work out a scale on here. And this point, 30 megameters, okay? And we also know that the gravitational potential that we calculated earlier on the Earth's surface, and when I said it was for me, the potential is for any object, okay? It will, because it's the number of joules per kilogram of that object, will be down here at about minus 63 rounded up megajoules per kilogram. Okay, so this point here, yep, this point here, 6.4 megameters is the radius of the Earth. So I'm just going to come down like this and say we know the gravitational potential at that point, and we also know that Vg is equal to minus Gm upon r. So we can draw a curve that kind of shows this relationship, a dropping off with 1 over r. So I'm not drawing this accurately or doing any numbers. I'm just kind of doing it diagrammatically. Okay. So, because if you calculate it, I might not be quite in the right place. So I hope you can see now how I've built up that graph. Okay. And there's a couple of things to point out. That if we go that way, Okay, if R goes that way, yep, we have an increase in the amount of gravitational energy we're giving something. Okay, so an increase in Vg, and what I mean by that, of course, is it's less negative. Okay, and obviously if we fall in towards Earth, there's a decrease in Vg. Okay, but I'm being careful what I mean by that. The Vg number goes up, doesn't it? But it's negative, so you've got even less gravitational potential energy. So maybe pause there and see if you can get your head around this graph and how I managed to sketch it. And clearly I'm not messing around here because we haven't talked about the nature of the field inside the Earth. Okay, but in a minute we need to do this a little bit differently, because of course if we're rocket scientists, the likelihood is we're going to be going from one large gravitational mass to another one, like from the Earth to the Moon, or maybe in my lifetime, or even yours, probably yours, going to Mars. So this diagram needs to change, because we are being attracted towards the Earth here. But what happens if, where my pen tip is, there's another mass attracting you towards it? So what we'll do next is look at a situation with multiple masses. So I did say, what happens if we have multiple bodies? Okay, let's keep it simple, maybe the Earth and the Moon, but there may be more objects we need to take into account. So if we put a pinprick in the map and say, okay, what's Vg at that point? We've got to take into account all the masses that do attracting. Now, obviously, you're not even going to begin to draw some kind of field line shape. That would be either very complex or really, something that wouldn't help us understand it. But remember, Vg is a scalar. And that's the key to this one. So all you do, because it's a scalar, is add the Vg values, the Vgs, of each body, each mass, at point R, at the point you're at. Okay, so that could come up at A level, I guess. They could give you a number of objects, okay, and they could give you their masses, and I put a pin in the map. So just calculate what Vg is from that one, and add it to that one, and add it to that one, and add it to that one, because it's a scalar, so we can just add the values at any point. So finally, let's do a multiple body one, or at least schematically, as it were, and it's obvious we should do the Earth-Moon system. So, Earth, Moon. Right, so I'm going to do this graphically, and I hope you remember what I've got to do here. So I'm going to draw my axes, remembering that Vg is a negative value. So here we go. And it's good to build this thing up in front of you. I'm off on a tangent now, but I was always taught by the guy who taught me at school, who was absolutely brilliant. He said, set up every piece of apparatus in front of your pupils so they can see how it goes together. And the same with this. I'm not going to just flick a PowerPoint slide up. I'm going to build it in front of you. So, because you'll have to do the same one day, maybe. So here is our R-axis, and here is our Vg, axis, and we're going to position the Earth here. So there's the Earth, and over here, at that point there, let's have the Moon. Okay, we're going to remember that the Earth does have a radius, and we're only interested in this case in going sort of above the Earth's surface, but of course R is measured from the center of the Earth. Okay, So, you remember I dropped down to here to give the VG value at that point, and I'm not going to put a number on it. Okay, you could do that, because remember that it's a multiple body system now. So this is not the value for the Earth, it's the value for the Earth summed to the Moon. Okay, and now I'll put the line on, and I'll try my best to sort of draw this as well as I can. Okay, it's going to drop away like this, and then it's going to rise again. Okay, so a couple of things to note about this. Yep. Firstly, yep, because VG is a bit more of a curvature we need there, really. But VG is negative, so when we're in this region, yep, you need a force is needed to sort of pull away from Earth. Okay, and then there's a point here, look very carefully, closer to the Moon, further away from the Earth, but it's not going to be zero. Okay, it's so tempting, I'm disappointed with that, should be a better curve, so tempting to put that point on the zero of VG. It can't be, because it's not infinity. Okay, but if you think about it, the gravitational field of the Moon is going to have quite an effect close up. Okay, so this is not zero. And finally, look at what's happening here. Okay, that represents the fact that when you get that close, you will fall into, you know what I mean, the Moon. Okay, not into the Moon, but you'll fall towards the Moon. So have a look at that diagram. You might want to put numbers on it. It might be quite an interesting thing for you to try and do. Okay, but look at the salient points, the important bits. Particularly, there's a place where if you released the spacecraft from sort of stationary, it would fall to Earth. And if you released the spacecraft a bit closer from stationary, it would fall towards the Moon. So I do hope you enjoyed that lesson, and you now feel you have a better understanding of gravitational potential. Okay, do have another look over it and maybe make some notes so you're sure that you understand it. This is not something to have a sort of ish understanding of. You need to come away from it going, yeah, I've got those points and I understand what they mean. I could explain it to someone else. Okay. Now, if I've got it right, I've got one more lesson to make for you on gravitational potential energy, and then we've finished the gravitational fields chapter. So I look forward to seeing you again next time.